Linux buffer overflows. In this module, we'll introduce Linux buffer overflows by exploiting Crossfire, a Linux-based role-playing game. Specifically, Crossfire 1.9.0 is vulnerable to a network-based buffer overflow when passing a string of more than 4,000 bytes to the setup sound command. In order to debug the application, we'll use Evans Debugger, which provides us with a familiar-looking debugging environment. About dep, ASLR, and canaries. Recent Linux kernels and compilers have implemented various memory protection techniques, such as data execution prevention, address space layout randomization, and stack canaries. Since the bypass of these protection mechanisms is beyond the scope of this module, our test version of Crossfire has been compiled without them. Replicating the crash. Our test environment will consist of a dedicated Linux Debian lab client, where we'll run and debug the vulnerable application, and our local Kali Linux box, where we'll launch the remote exploit. In order to replicate the crash, we'll first desktop to our dedicated Debian Linux client. Once connected, we'll launch a terminal via the System Tools menu and run Crossfire. Once Crossfire has launched, it will accept incoming network connections. Next, we'll launch the Evans debugger by running the edb command. The layout of edb is similar to other popular debugging tools. To see available processes, including the PID and owner, we'll select Attach from the File menu. We can then search for our Crossfire process, select it, and click OK to attach to it. When we initially attach to the process, it will be paused. To run it, we can simply click the Run button or press F9. Now that we've attached the debugger to the Crossfire application, let's examine the proof of concept code that we created based on information from the public exploit. Notice that our buffer variable requires specific hex values at the beginning and end of it, as well as the setup sound string, in order for the application to crash. Our initial proof of concept builds a malicious buffer, including the setup sound command, connects to the remote service on port 13327, and sends the buffer. To crash Crossfire, we can run our first proof of concept using Python. After running the script, the debugger displays an error message, clearly indicating the presence of a memory corruption in the setup sound command, likely a buffer overflow condition. After clicking the OK button, we find that the EIP register has been overwritten with our buffer. Before we continue, let's restart Crossfire and launch edb and attach to our Crossfire process. Controlling EIP. Our next task is to control the EIP register. To do this, we must identify which 4 bytes in our buffer end up overwriting the vulnerable function return address. We'll use the Metasploit MSF pattern create script to create a unique buffer string. To keep our buffer length consistent during the exploit development process, we'll specify a pattern length of 4,379 bytes. Let's add this unique string to our next proof of concept. This pattern will be sent to Crossfire instead of our string of A's. Let's run the proof of concept and find out which bytes overwrite EIP. As expected, Crossfire has crashed. This time, EIP has been overwritten with bytes from our unique pattern. After noting this value, we'll restart Crossfire and EDB once again. Now, let's find out where those 4 bytes occur in our pattern. Passing the 4 hex bytes to MSF pattern offset tells us that the pattern was found at offset 4368. To confirm this offset, we update the crash variable in our proof of concept to cleanly overwrite EIP with 4 B characters. Now we'll run the script and hopefully verify our control over EIP. Excellent. EIP is cleanly overwritten with our 4 B characters. Locating space for our shellcode. Next, we must find if there are any registers that point to our buffer at the time of the crash. This step is essential, allowing us to subsequently attempt to identify possible jump or call instructions that can redirect the execution flow to our buffer. We notice that the ESP register points to the end of our buffer, leaving only 7 bytes of space for our shellcode. Furthermore, after a bit of experimentation, we determined that we can't increase the overflow buffer size in an attempt to gain more space. Even a single byte increase produces a different crash that does not properly overwrite EIP. Taking a closer look at the state of our registers at crash time reveals more options. The EAX register seems to point to the beginning of our buffer, including the setup sound string. The fact that EAX points directly to the beginning of the command string may impact our ability to simply jump to the buffer pointed at by EAX, as we would be executing the hex opcode's equivalent of the ASCII string setup sound before our shellcode. This would most likely mangle the execution path and cause our exploit to fail. Or would it? Further examination of the actual opcodes generated by the setup sound string reveals some interesting instructions. It seems that the opcode instructions for the first 2 letters of the word setup, S and E, translate to a conditional jump instruction, which seems to jump to a nearby location in our controlled buffer. The next 2 letters, T and U, translate to a slightly different conditional jump. All these jumps seem to be leading into our controlled buffer, so a jump to EAX may actually work for us in this case. However, this is not an elegant solution, so let's try harder. Continuing our analysis, it looks like the ESP register points towards the end of our unique buffer at the time of the crash, but this only gives us a few bytes of shellcode to work with. We can try to insert a first stage shellcode into that limited space. Rather than an actual payload such as a reverse shell, this first stage payload will be used to align the EAX register in order to make it point to our buffer right after the setup sound string, and then jump to that location, allowing us to skip the conditional jumps. In order to achieve this, our first stage shellcode would need to increase the value of EAX by 12 bytes, as there are 12 characters in the string setup sound. We can accomplish this with an add assembly instruction, and then proceed to jump to the memory pointed to by EAX using a jump instruction. In order to get the correct opcodes for our instructions, we'll use the MSF NASM shell utility from Metasploit. Fortunately for us, these two sets of instructions take up only 5 bytes of memory. We can update the proof of concept by including the first stage shellcode and re-padding the original buffer with NOPs in order to maintain the correct length. Let's give this new proof of concept a try. Our updated proof of concept code is working perfectly. The EIP register is overwritten with 4 Bs, and our first stage shellcode is located at the memory address pointed to by the ESP register. Checking for bad characters. To discover any bad characters that might break the overflow or corrupt our shellcode, we use the same approach as we did in the Windows Buffer Overflow module. We sent the whole range of characters within our buffer and then monitored whether any of those bytes got mangled, swapped, dropped, or changed in memory once they were processed by the application. After running the proof of concept multiple times and eliminating one bad character at a time, we came up with a final list of bad characters for the Crossfire application, which only appear to be 00 and 20. Finding a return address. As a final step, we need to find a valid assembly instruction to redirect code execution to the memory location pointed to by the ESP register. The EDB debugger comes with a set of plugins, one of which is named Opcode Searcher. Using this plugin, we can easily search for a jump ESP instruction or equivalent in the memory region where the code section of the Crossfire application is mapped. We choose to proceed using the first jump ESP instruction found by the debugger. We're getting closer, so let's restart everything before we continue. Before we work on our next proof of concept, let's set a breakpoint on our jump ESP return address. We can do this with the EDB Breakpoint Manager plugin. We'll click Add Breakpoint and paste in the address of the jump ESP instruction. With our breakpoint set, we'll let the application run and return to Kali. Putting the overwrite offset, return address, and first stage shellcode together gives us our next proof of concept. With the breakpoint set, we can run the proof of concept. If everything has gone according to plan, our debugger should have stopped at the jump ESP instruction. The breakpoint has been hit. Now we can proceed to single step into the jump ESP instruction and land at our first stage shellcode. After executing the initial first stage shellcode instruction, we find that the EAX register now points to the beginning of our controlled buffer right after the setup sound string. Once the EAX register is aligned by our first stage shellcode, a jump EAX instruction brings us into a nice, clean buffer of A's. We're nearly finished, so let's restart and reattach. Getting a shell. All that's left now is to drop our payload at the beginning of our buffer of A's, reachable through the first stage shellcode. We'll use a reverse shell as our payload and generate it using MSF Venom. We'll pass -p to specify the payload, followed by values for lhost and lport. We also specify the bad characters to avoid with the -b flag, the output format with -f, and the variable name to use with -v. Let's take a look at how this payload is added to our final proof of concept. Our payload is placed towards the beginning of our buffer, which means that we need to take the payload size into account and pad it with the correct amount of A characters. This will ensure that we maintain the original offset in order to overwrite the EIP register with our desired bytes. Before we launch our final exploit, let's open up a new terminal and set up a netcat listener to catch our shell. Now let's send our exploit. We've received a connection on our netcat listener. However, the shell appears to be stuck. Going back to our debugger window, it appears that the application is paused. When we attempt to let it run, we receive a message regarding a debug event. Clicking OK on the event and going back to our netcat listener solves the problem. However, every time we run the exploit, we would have to repeat this process. This is because the debugger is catching SIG child events. When the child process spawned by our reverse shell generates a signal, for example, when the process exits, crashes, stops, etc. To ensure that our exploit is working as intended, we'll restart the Crossfire application and run it without a debugger attached. Now let's try running our exploit again. As we suspected, running the application without a debugger attached provides us with a working shell from the victim machine. Wrapping up. In this module, we covered the process of exploiting a buffer overflow vulnerability on a Linux operating system. Similar to the exploit used in the Windows buffer overflow module, we were able to debug a crash in a vulnerable application and write a fully working exploit for it.